Hello boys and girls. Today we will see the next topic of the oscillation. We are going to study about the oscillation. Last time we have seen the introduction part of the oscillation. Oscillation means vibrations or vibratory motion, or it is also named as the simple harmonic motion. So last time we have seen what is mean by the simple harmonic motion. What is mean by the simple harmonic motion? It is a periodic motion. Simple harmonic motion is a periodic motion in which the force or acceleration is always directly proportional to the displacement of the particle from the mean position and always directed towards the mean position. So last time we have seen the introduction part. Let's see the next topic, and that next topic is differential equation of simple harmonic motion. So let's see the equation for simple harmonic motion, but that equation is like differential. Differential means derivative form. So differential equation of simple harmonic motion. So before starting the expression, let us see the figure in which the particle is performing simple harmonic motion. So in this figure, this is the particle P performing simple harmonic motion, in which this is the point which is called as the mean position, or the point where the particular body will not experience any force, or which is initially present at that position where the resultant force is 0. So this is called as the mean position, and while performing simple harmonic motion, this is the one of the position at the right hand side where we get the maximum displacement is called as the extreme position at the right hand side. On the other hand, at the other side, there is also a point where the particle shows or describes the maximum displacement, and that point is also called as the extreme point or extreme position. So in simple harmonic motion, there is one position at the center which is called as the mean position, and the two positions called as the extreme position. So let us see, while performing simple harmonic motion, suppose the particular body is present at point P where the displacement of the particle is x from the mean position. This is the mean position, and from this mean position the particle is here. Suppose that displacement is x. Displacement is x, and displacement is right handed directed. Then at position P, the particle will experience some certain force, and that force is directed towards the mean position. Suppose at position P, the particle will experience force F, and this force F is always directed towards the, or always directed, or always directly proportional, not directed, always directly proportional to the displacement of the particle from the mean position. So from the definition of the linear simple harmonic motion, we know the force is directly proportional to the displacement and always directed opposite direction to that of the displacement. That means the directed towards the mean position. So we can write equation. Last time we have seen, in linear simple harmonic motion, force is directly proportional to the displacement with opposite direction. So we can write F is proportional to minus x. That is, F is equal to minus kx. What is k? K is force constant. K is force constant. So this is the equation. By the definition of the linear simple harmonic motion for the force. Now write another equation according to the Newton's law of motion. So we know, according to the Newton's second law of motion, force acting on the body is always equal to the product of mass multiplied by acceleration. Place this value in the previous equation. So instead of force, we can write here ma, and then equal to at the right hand side, right as it is minus kx. So this is the equation number 1 and this is the equation number 2. So let's see. In this simple harmonic motion, the particle is performing simple harmonic motion, and at every position particle will have some velocity. But at different position the particle has a different velocity. But we have considered a position, a single position P, where particle has some certain velocity, and that velocity is v. Velocity is v. Also there is acceleration. Acceleration is indicated by a. So particle which is present at p position, it has the velocity v and it has the acceleration. So we can express the velocity and acceleration in differential form. We know the velocity. What is meant by the velocity? Velocity is the rate of change of displacement with respect to the time. And what is meant by the acceleration? Acceleration is the rate of change of velocity with respect to the time. Write the two equations for the velocity and acceleration. So here velocity of the particle is v, and v means velocity. It is defined as derivative of the displacement with respect to the time. That means the change in displacement divided by change in time. So displacement divided by time means rate of change of displacement with respect to time. That means the velocity. So we can write velocity in the differential form. So dx by dt. Dx by dt means rate of change of displacement with respect to the time. Similarly, write the acceleration. Acceleration a. It is also rate of change of velocity with respect to time. Rate of change of velocity with respect to the time. But velocity means dx by dt. Write the value of v. Here we get d2x by dt square. So velocity, then acceleration, and acceleration can be written in this form, that is the differential form of the acceleration. So acceleration is equal to now dv by dt. Again placing the value of v, we get d2x by dt square. So this value for the acceleration we have to substitute in this equation number 2. Then equation number 2 becomes, then substituting in equation 2 we get mass. Instead of acceleration, right here d2x by dt square, d2x by dt square is equal to, right hand side will be same, minus kx. Then divide this equation by m, mass, on the both sides. So mass will get cancelled, remaining d2x by dt square, d2x by dt square. Now at the right hand side divide by m. So k by m minus k by m multiplied by x. So again in the next line d2x by dt square, change the sign, we get the plus sign. So k by m x is equal to 0. So this is the third equation. In this equation the ratio k by m can be written as omega square. So in the equation 3 substitute the value for k by m, and the value for k by m is omega square. That we discuss in the next or later topic next time. Substituting the value for k upon m, and which is the omega square. And what do you mean by omega? Angular velocity or angular frequency of the body performing simple harmonic motion. So omega means angular velocity or frequency. Place this value instead of k upon m, so we get d2x by dt square plus sign, then k upon m means omega square. So omega square multiplied by x is equal to 0. So equation number 4. So this is the differential equation of simple harmonic motion. So this is the very important equation we have to remember for or while discussing the next topics. Thank you.